Okay, good morning. Let us resume our discussion. What were we discussing in the last class? Any quick points? What is that we were discussing in the last classes?
We were discussing about scale and variant feature transplants.
Right.
And the various steps for extracting key points, starting from scale space to localization. And then we ended our discussion on localization, where we expanded through the Taylor series, the expression of D, and classified whether key point is weaker.
Right, good. So we have expanded in Taylor series, and then we can find the in the proximity of the key point that we have identified coarsely in the previous step in this through scale space. Now we can exactly localize even to a subpixel level through this. Okay, because what you get from here, what the solution you get will be a non-integer solution. So it will be at the subpixel level. Usually X, if it takes only pixel level, XY, if they take integer values, it is at the pixel level. Okay, if XY takes even fractions, then we can consider it as a subpixel level of identification. Okay, so what you can see here is we can get to the subpixel level, estimation of the exact location of the key point. And at that location now, the difference of Gaussian values, if they are greater than a threshold, we consider that it is a good key point. Okay, if it is less than threshold, it is a small, not very good key point or weak key point, and it can be ignored. Threshold usually, if I remember correctly, it is put as 0.04 or something like that. Okay, we'll see the exact values in the slides. Okay, so by this we can eliminate the weak key points. Then the other thing is, even in the scale space representation, and when we want to see the maxima or minima in the Laplacian of Gaussian values, we can still get the some of the edge pixels also in. So if you would like to eliminate the edge pixels, do you people have any idea? So did we anytime had a procedure to eliminate the edge pixels versus the corner pixels? Did you remember of any other technique where we have taken some clue of some of the properties and then eliminated the edge pixels and the corner pixels, or differentiated the corner pixels and edge pixels? Where did we discuss before? On
the Harris corner
detection.
Right, in Harris corner detection. So what did we do there? There was a matrix M which takes ix square, okay, ix iy, okay, and then ix iy again, or iy ix and iy square, okay, and then takes this decomposition into lambda 1, okay, whatever, lambda 2, okay, into whatever, and then using these eigenvalues we can identify which are edge pixels. What is the condition for an edge pixel in terms of eigenvalues, or what is when we can say a pixel is edge pixel, or when if we identify a key point, for what values of lambda 1 and lambda 2 can we say that it is an edge? Based on this is in Harris corner detector only I am discussing.
If one lambda 1 is very high, another is very low, so we can say that it is an edge.
Right. So if lambda 1 is very small compared to lambda 2, or lambda 2 is very small compared to lambda 1. Okay, one of them is very small, and the ratio of lambda 1 by lambda 2. Okay, if we consider lambda 1 as the minimum value, okay, among lambda 1 and lambda 2, then minimum being lambda 1, the ratio of lambda 1 by lambda 2 also is an indicator of how much edginess it has. Is it not? Because what does lambda 1, lambda 2 characterize? Why are we discussing based on lambda 1 and lambda 2 for the characterizing edges? What are lambda 1?
They characterize the spread of variance in two directions.
Yeah, they characterize the variance of the intensity distribution in two different directions, two orthogonal directions. Okay, one in the maximum, one in the minimum direction. Minimum distribution or minimum variance and maximum variance. Okay, and if both are both directions has high variance, then we say it as a corner pixel. If one direction has a good variance in the intensity distribution, and in another direction, if there is a weak intensity distribution, then we say that it is a edge pixel. Similar way here in the scale invariant feature transform, what these have adapted, what that Professor David Lowy has suggested or adapted is based on the difference of Gaussian. Since we already have difference of Gaussian, can we make use of this rather than finding out the edge pixels or the finding out differentiating the edge pixels from the corner pixels through the matrix M, which is based on gradients. Okay, so the idea here also in similar lines. So we construct a Hessian matrix. Okay, Hessian matrix, as I probably discussed before, is a second order derivative matrix. So it is with the dxx, that is second order derivative in x direction, dxy and dyx. Okay, and then dyy. Okay, where dxx corresponds to dou square d of x, okay, by dou x square. Okay, and similarly dxy dxy corresponds to dou square dx. Dx, please note that xy sigma all are there in capital X. Okay, x, y, and sigma. Fine. Dou x, dou y. Okay, this is how we construct the Hessian matrix. This is referred to as Hessian matrix. This is with second order derivatives, as you can see here. And anyway, dyy in similar lines, dou square d capital X, okay, by dou y square. Once we have the Hessian matrix like this, and if we see now the eigenvalues of this matrix, okay, anyway, for decomposing into eigenvalues, you may need to have the eigenvectors also. But now we are not discussing too much on the eigenvalues. The reason that we will just see. Okay, so if we decompose this Hessian matrix into the eigenvalues, then in similar lines for an edge, what's supposed to happen? The one of the eigenvalue will be much different from the other eigenvalue. That means one will be smaller or one will be larger than the other eigenvalue. See, in discussion, while discussing the Harris corner detector, did we explicitly find the eigenvalues to identify whether it is an edge or a corner and so on? Or what did we make use of?
We defined a parameter R.
We found a measure R, which is composed of
determinant and trace.
Right, determinant and trace. Is it not? So this is encompasses lambda 1, lambda 2 minus k times lambda 1 plus lambda 2 whole square. Right? So in some sense, what did we make use of? Determinant gives if both eigenvalues are high, then the determinant will be high. That is the idea here. And if both eigenvalues are different, then trace will be high. Okay, if one of them is much higher than the other and so on, okay, that in such case trace will be higher. So what it indicates, if both are similar or both are high, okay, then the value of this and this both will be, okay, this will be high and this will be low. Not as high as one being very high and other being very low. Okay, so in such case, we can essentially have this expression, this will be much higher, or otherwise, if both value lambda 1 and lambda 2 are higher, lambda 1 into lambda 2 will be much higher than lambda 1 plus lambda 2. Okay, that property is being seen here. And based on that, we have quantified the cornerness index, and then that's what we have used. Even here, here also we would like to use the similar principle. Just that instead of using the difference here, if I want to use for an edge pixel any other measure, Okay, so some measure for an edge pixel. If I would like to put in terms of another r dash, I may call now just now. Okay, so if I would like to put in another measure in terms of the eigenvalues, but without computing the eigenvalues, what kind of measure can I put? I don't want to use the difference now. Okay, I would like to use slightly different way of using, but still I don't want to compute eigenvalues. Not to compute eigenvalues, what is the better way to use? So if I don't want to compute eigenvalues, still compute a measure where lambda 1 and lambda 2 are much higher than the lambda 1 or lambda 2 alone, then what should I use? What should we use? See, if you would like to make the identification of an edge, lambda 1 and lambda 2 will be like one of them will be much higher. For a corner, both will be higher, right? So without computing lambda 1 and lambda 2, if I would like to use the eigenvalue, not explicitly computing eigenvalues, but I would like to use the knowledge of eigenvalues to identify whether it is an edge or not. What is that we should use?
Trace and determinant.
Yeah, determinant and trace. So we would like to use slightly in a different way. Any other suggestion on how can we use without say taking the one minus the other and so on? So
divide them, take a fraction.
Can you repeat a menu?
Taking a fraction, sir, like
Yeah,
division
taking
of
the
both.
fraction, that's all. So lambda 1 plus lambda 1 lambda 2 by, okay, so you can take that determinant by lambda 1 plus lambda 2 whole square. Okay, so there is no need of k also now in this. So if we consider this, say we can also rewrite this as lambda 1 by lambda 2. Okay, so I am just taking lambda 2 square out, okay, from the numerator and denominator. Lambda 2 plus 1 whole square, right? So I can rewrite the same like this. And if we write this lambda 1 by lambda 2 as small r, where the value, the minimum eigenvalue is lambda 1. In such case, r will be less than 1, right? So now this RH now can be rewritten as small r. Sorry, it's other way. So we can even use this also, but they have used in the other way. So here it value has to be high. In this case now, value has to be low. Because if value has to be low means it, if we can easily put a threshold and say that below this value, we consider it as a corner point. Above that value, it is an edge point. So I'm just taking lambda 2 square out. Okay. So this is written now as what? R plus 1 whole square by R. Now, what is the value for R? What is the range of R? Given that lambda 1 is much smaller, is smaller than lambda 2. If we assume that lambda 1 is smaller than lambda 2, okay, even much smaller or smaller, it doesn't matter. So if smaller or equal, okay. So in the worst case, it is equal. So given or taken for the generality of notation, if we take like this, now the measure, now what we have is R plus 1 whole square by R. Okay, and then here what is the R value? Lambda 1 by lambda 2. And what is the range of this? See, this is a positive semi-definite matrix. In fact, it becomes a positive definite matrix. So eigenvalues will always be greater than or equal to 0. Okay, or greater than 0 strictly. So in that case, lambda 1, lambda 2 both will have same sign. If both have same sign and lambda 1 is smaller than lambda 2, what is the range of this?
0 to 1.
0 to 1, right? So since now, what is the range of RH now? So if both of them are say 0 to 1, what is the range of RH now? So R can take a maximum value of 1. So it is 1 plus 1 whole square by 1. So this is actually 4. If R takes a very small value, okay, when R takes a small value, when does R take a small value?
When lambda 2 is very much higher than.
Right. So in such case, say lambda 1 is very smaller than lambda 2, it means that it is a, if R is very small value, okay, then what can happen? So it is say 1.1 whole square, which is close to say 1.21, right? By 0.1, so it is 12.1. Okay, so this is actually, this RH now is much higher than this. So for if we would like to use RH and put a threshold to say that whether it is an edge pixel or a corner pixel, how should I use this measure as a measure? This is the case where lambda 1 is lambda 1 by lambda 2 is equal to 0.1 or lambda 1 is smaller than lambda 2. Okay, so this is the case, that this is that case. Here this is the case where lambda 1 is equal to lambda 2. Okay, given this, now for an edge pixel, I would like to put use RH and put a threshold on that. What do you suggest? Okay, or for corner pixels, for edge pixels or for corner pixels, we can say. Corners are key points. RH has to be how much? Should I put, say if I put a threshold being 10, okay, some threshold I can put. Should it be less than or equal to or greater than or equal to? For a corner pixel or for a key point, potential key point, should it be less than or equal to 10 or greater than or equal to 10?
Less than.
Yeah, it has to be less than or equal to. No, because if it is greater means what? Lambda 1 and lambda 2 differ much. Okay, in such case, RH will be higher. Okay, so they have put a threshold of 10, and if it is less than or equal to 10, it is considered as a potential key point. Okay, so this eliminates the edge pixel. Okay, being selected as key points. Fine. So this by this what we have done is we initially started with getting the key points from the scale space constructed by difference of Gaussians. Okay, in the peak locations of the scale space is what we have considered as the key points. And from there we eliminated we have localized the key points, and then weak key points are being eliminated. And through this step, we have identified whether this key point is potentially corresponds to the corner point or the edge point. And then we eliminated even the edge points or the points that are tending to be edge points. That means you cannot distinguish them very well, okay, in all directions. Or the variance in all directions is not high, probably in some of the directions is much higher than the other directions. Okay, so such elements are such outliers or the non-potential key points are eliminated. Now the next step is, say we have identified the key points at different scales. So each key point that is identified now is associated with a, say if I identify a key point at a particular location xy and with a scale, I associate a key point x, y, comma, sigma. This key point might have identified at xy in another xy and k times sigma in another scale. Okay, so the another key point might be located at another scale. So x, say if we consider this as x1, x1, y1, x2, y2, okay, and then x3, y3, and then sigma 3. Okay, so another sigma, k square sigma, whatever. Okay, so each key point now is associated with a xy values and a particular scale at which it is identified as the key point. That will help us in matching also, because if we match, when we are trying to match across the images, so in similar looking images, we assume that the key point also appears at the same scale, and it helps us to match with a better check on the scale as well. Further, it helps us to see at what scale we have identified a key point, and the size of the object or some such things also can be inferred. Okay, so now the next thing that is left is, see, the object may be in any way. So if we identify a key point, it has to be associated with or assigned with a direction. Because what will happen if I just want to find out two objects which are similar looking, but they are oriented differently in two different images, then what will happen? So if I don't identify with the description around the key point with respect to a particular orientation, I may miss the matching, appropriately matching this patch versus this patch. Okay, both are same, but except that this is oriented in this direction, okay, and then this is oriented in this direction. The direction is only the difference. So if I can associate a direction also to the key point, okay, that has two advantages. One thing is, anyway, direction is needed when, since we discussed before, the good descriptors for around the key point. That means once we find the key point, we need to describe it by the around the patch around the key point, and that patch has to describe the features of that patch has to be described in a such a way that they are invariant to the scale, they are invariant to the rotation, they are also invariant to the viewpoint, they are also invariant to the photometric changes like intensity variations, contrast, okay, and then color variations, all those aspects. Okay, so if you would like to get such a robust descriptor, what we have seen is histogram of orientation gradients is one of such descriptor. So histogram of orientation gradients depends upon understanding or first assigning the gradients, angle of gradients, and using the angle of gradients for describing the patch. So anyway, angle is being used in the describing the patch or the patch around the key point or the key point itself. So can we measure these angles with respect to a standard angle or a reference orientation? That is the question, and that is being taken care in scale invariant feature transform. So now if you would like to first arrive at the reference orientation or even to extract the histogram of orientation gradients, what is the starting point? Given an image, okay, and we also have some object, okay, and what we also have some key points now, location of key points. Okay, then the next question is, after we get the key points, we would like to get the histogram of orientation gradients kind of descriptor. Okay, so this is not referred in generic way. It is not explicitly referred as histogram of orientation descriptor in scale invariant feature transform. Okay, so they also has, but see, it looks quite similar to that. Also, we would like to have a descriptor essentially, shape-based descriptor, which is invariant to all those aspects. Okay, so now where should we start? So this is the image I is given to us. Okay, and we need a descriptor. What is the next step? We should compute what? To get the angle-based description or the histogram of orientation gradients-based description. What do you think is the next step? Take a patch around here. It is unlike the whole image. Now you take the patch around each key point. Okay, take a patch around each key point. Let that patch be say 4x4 or whatever. So a standard dimension, 4x4. 16x16 or whatever. You can have a standard dimension for that patch. Around each key point, let's take a patch. Okay, the patches may be overlapping as well. Now, after taking the patch, what we need to do is around the key point first, we would like to calculate the gradient in x direction and gradient in y direction. Okay, so how do we calculate the gradient in x and gradient in y directions? We can calculate anyway using the, right? So how to calculate? You can use any of the filters or the kernels to find out the gradients in x and y directions. So to find out gradient in x direction, so if I think they might have used central difference operator. Okay, and we can use this. So this is for ix, computing ix. Okay, convolution with this will give us ix. So this is filter in hx I will call, and this is hy. Okay, so ix you obtain by convolving image with the hx, and then iy you can obtain convolving image with the hy. Okay, so once you get this, you can also write this in terms of the say the expressions, okay, that you will see in the slides. And after that, we would like to get the gradient magnitude, okay, and gradient angle. Okay, so how do I get the gradient magnitude? Ix square plus iy square and the square root, and then gradient angle tan inverse of iy by x. Once we get the gradient angle and magnitude, okay, what do we do is for this patch, okay, we decide the number of bins. Okay, so assume that for this, say if it is 8x8 patch or 16x16 patch or 4x4 patch, we can decide the number of bins. So if number of bins, assume that the number of bins decided are 18 or 10 bins. Okay, I think in HOG they use 10 bins. In SIFT they may use 10 bins. Okay, so 10 bins. So if we are considering 0 to 18, okay, 180, then this comes each is 18 degrees angle. Okay, so here a priori bins are decided. If we decide 10 bins, then this is the angle we take. For each 18 degrees, what we do is we find out the number of, we need to construct the histogram of orientation gradient vector. Okay, that is the next step. So now what is necessary is, see, assume that you have a small patch here. Okay, so I just take a 3x3 patch for easy understanding. And here in 3x3 patch, assume that the angles are given and as well as the magnitude are also given. Okay, so this is the magnitude IG and these are angles. So the in scale invariant feature transform, they used both magnitude and angles together to construct the histogram of orientation gradient vector. That means, say if the assume that angles are 5 degree, okay, 20 degree, and then 15 degrees, 80 degrees. Okay, I'm just putting arbitrarily some value, 45 degrees, and then maybe 60 degrees, okay, 75 degrees, and then 90 degrees. And then all are say within, right? So 120 degrees. Okay, let these be the angles. And for our simplicity, let us assume that each bin, okay, we have total 10 bins, right? 18 degrees we have taken, but let us take each bin is say 22.5 degrees, okay, per bin. So how many bins you will get? So 9 bins, right? Is it not 9 bins? So 0 to 45, 90, 4 bins and 4 bins, 8 bins. Yes or no? So 22 degrees per bin if we consider, 8 bins we get for spanning 0 to 180 degrees. Right? Now assume that the magnitude values are also given. So magnitude values are such that here it is 100 gradient magnitude. Okay, here it is say 80, okay, and then 60, and then 45, okay, and then probably 60, and then 5, 10, and then 2, and probably 20. Okay, these are the gradient magnitudes. Now, how do they construct the histogram of orientation gradient vector is? So we separate this 0 to 180 into bins. Okay. How many bins now? 8 bins. 22.5 and then 45. 45 plus 22.5. So that is 67.5 and then 90. 90 plus 22.5. Okay. So now for each bin, how do they calculate the height of the HOZ? Is the angle, at that angle, we see the corresponding gradient magnitude and sum them. So in this bin, say for example, 0 to 22.5, which are all the angles that fall in 0 to 22.5? How many, say if I don't consider a gradient magnitude, how much should be the height of the HOZ here? For the first bin, how much should be the height?
70.
No, if I don't consider the first magnitudes, it is only 3.
3.
Yes.
Right. If I consider the magnitudes, then what I do? I will sum the magnitudes corresponding to that and then write that value. So in that case, it will be 70. Correct? 10 plus 5 plus 2, 70. Now 22 to 45 degrees. Assume that 45 degrees is also inclusive. Okay, then 22 to 45 degrees. How much we get? What is the height? What is the height?
60.
60. Okay, please don't take this to the scale. Okay, I'm just roughly sketching to get an idea for you. Okay, and then what is 45 to say 67.5? Okay, what's the height now? 45 to 67.5. How much is the height? I request you people to see so that you can easily understand how do we construct the histogram of orientation. Yeah.
45.
Oh, 45, correct. So it's 45. And 45 is 67.5 to 90 now. 67.5 to 90. So you have actually 4 pixels with those angles coming into the this bin. And then their corresponding heights are 45. Oh, 60 already is there, right? So then 80.
160.
So how much is that?
160.
160.
It is 160. Very good. Okay, and then 90 to 111.5. In this bin, how many will come? 112.5. How much is the height of this bin?
0. No,
Oh, it is
nothing.
0. It is 0. Okay, and then 112.52. Again, how much? 135, right? 135.
100 will.
100.
100, very good. So it's 100. Okay, and then 135.52. What is the next one? 157.5. 157.5. What is the height? How much? It is?
Next all will be 0.
All rest is 0. Right. That's all. Okay, so this is what is 100. Okay, it's not. So you can see that HOZ is considered like this, wherein both the magnitude, gradient magnitude and angle is all are considered together. What is the rationale in considering gradient magnitude? Say, should we consider gradient magnitude also while sketching the HOZ or while considering the HOZ vector? Or should we only consider the gradient angles? Or the count of gradient angles we have to consider? What do you think is correct procedure? Which one will you vote?
I guess magnitude, sir, because if the magnitudes of the angles are counted, then more prominent and features will come.
Yeah, that's true, but more prominent features will come true. But why should we consider? Why do they help in getting better prominent features is the question. What is the intuition with respect to the image in considering magnitudes as well? Your answer is correct, but I need another supporting statement in terms of an image. What does that mean? So this is the 8x1 HOG vector. Okay, so finally this comes as a vector, 8x1 vector. Okay, to be given to any classifier. For the key point, for each key point is described by now 8x1 HOG vector. Okay, as you can see here. This is the angle based description, but however here we have not yet considered this reference orientation. Okay, this is just a HOG vector without considering any reference orientation. So the reference orientation, if you would like to consider, the orientation that is dominant in this histogram of orientation gradients is considered as the reference orientation. That means, see, if I see a key point car here, car is moving this side, you can see that this may be the dominant orientation for the car. Okay, so what will happen? If I visualize it, as you have seen in the previous example, a human, when you visualize, okay, what will happen? So you can see that actually a human will have the dominant orientation around if this is 90 degrees, if we consider, the dominant orientation is along the vertical direction, that is 90 degrees. Okay, and then the next dominant is 45 degrees. But if you consider a patch, in this patch, 45 degrees is the dominant orientation. That's how we're able to show like this way, these vectors in the plot of human described by the HOG. Okay, so dominant orientation will indicate what is the shape information in that patch or around that key point. So the dominant orientation is the one, the peak in the HOG, that's all. So here dominant orientation, what is the dominant orientation? We can still consider it as, say, if you would like to put a value that is between 67.5 and 90, we can put that itself as the dominant orientation. Okay, so here we can consider this as the dominant orientation. This is the dominant orientation. So the dominant orientation here, reference angle here, is decided by the dominant orientation, and hence that is equal to, say, it's in between. So we have to add, I think, 11.25. Okay, so it will be 78.75 degrees. Okay, so the dominant orientation here for this HOG vector is HOG vector with dominant orientation of, or with reference orientation of 78.75 degrees.
So how did we take 78.75?
70, that comes because we are just trying to see which is the highest in the HOG, that which is the dominant orientation in that histogram of orientation gradient vector. So as I mentioned here, for humans, when I see a local patch, for the hand, this will be the dominant orientation. So it will be close to minus 45 degrees, will be dominant orientation. If I see a patch here, it will be, say, 90 degrees will be dominant orientation. If I consider, okay, 90 degrees as vertical. So if I consider a patch here, dominant orientation is close to 0 degrees. So like that, dominant orientation will give the shape information in that patch or in that around that key point. Okay, what it corresponds to? It corresponds to the gradient. Okay, it is, that's why the both magnitude and the angle are important. See, if you see this patch, this 3x3 patch, in this we have 3 pixels having a orientation of 5 degrees, 20 degrees, and 15 degrees falling into this bin. Okay, but this is not a dominant orientation because they are all weak edges. But if you see a 90 degrees edge, it's only a single edge. Okay, single in sense that only one has fallen into that, or say probably I think here also 3 has fallen into that, but those 3 have the high gradient values. Okay, so the dominant orientation is decided by the strength of the gradient magnitude and the angles together. Hope you people understand. Okay, so if there is a object with weak edges here and there, okay, that means many of the weak edges, if you see, they're all equal to 0 degrees now. Okay, so if we see 0 degrees everywhere, where there is no edge, if I consider it as 0 degrees, then all these have 0 degrees. But the strength of the edge is here is all 0. So I don't, if I construct a HOZ for the whole image as well, I don't see that the 0 degree is the dominant orientation. Okay, car here is 0 degree. So because of this, I may get the dominant orientation being 0. But otherwise, I will not get the dominant orientation as 0. I hope you got the point. Dominant orientation is the one which is the highest in the HOZ. Okay, and that we can use as the reference to represent the histogram of orientation gradients vectors.
So what do you mean by reference to the?
Yeah, right. Very good. So what do we mean by reference? Say, assume that now I have the same object, okay, which is described by this patch, but now it is rotated. Okay, so because of the rotation, assume that the rotation is fairly a good rotation. And then what I do is I see that the same thing. I just say this 3 cross 3. Whatever the patch here is rotated by say 45 degrees. Okay, 45 degrees this side. Now what will happen if the same patch, what say this car now is rotated by 45 degrees? What will happen instead of like this? The car is visible. Okay, something like this. Okay, I have taken with a camera which is straight in the first pic. Second pic is rotated 45 degrees like this. Okay, and the car is now like this. So now what happens? If I consider a HOZ in a patch, what happens? The HO angles all get added that 45 degrees to each of the pixels. Do you agree or not? So the magnitudes doesn't change, but the angles get added by 45 degrees because the magnitudes corresponding to that 45 degrees, the whatever magnitude you had now was there before without adding that 45 degrees. Okay, so now this will become the same thing which if I write in the next page, or if I try to write here itself just for ease of writing. Okay, just excuse me for writing small numbers. Okay, so it is say 40. Let us see if we can get this space somewhere. In the next slide, let's put otherwise. So what I'm saying is previously the object is like this. Okay, and you have considered a patch somewhere. Okay, for that patch we have noted. So if this is not a 90 degrees oriented one, let's take something. Okay, so assume that you take this. So we have a patch somewhere. Okay, for this patch I have noted before the whatever the angles I have got. Same angles. Okay, so 5, 20, 15. $80, $45, and then $60, $75, $90, $120. Okay, and I also have here the corresponding magnitudes. 5, 10 to 20, 60, 45, 60, 80, 100. Okay, so now this is the object patch I have considered, and for this patch, these are the descriptions. Okay, so now assume that I have taken another picture in which this object is rotated, okay, 45 degrees this side. Okay, so it's increased by 45 degrees. So the person is like this now. Okay, so same patch I have taken now. Okay, so previously you see it's like this, now it is like this. Okay, so now what we do is say this is the dominant angle, assume that previously it is the dominant angle, assume that this is close to this, and now this is not very well rotated, right? Let's rotate it. So this previously it's equal, the dominant angle that we have seen is close to 78 degrees. Okay, 78.75 degrees. Okay, or close to 90 degrees. Okay, that's what we had the previous dominant angle, as you can see here. Now, what has happened is he is say if this is the 0 degree, okay, he's rotated like this. So what has happened now? The person is like this. Okay, so this is the dominant direction now. Patch is like this, and the dominant direction is like this. Okay, so now if I see what happens, the angles all will rotate by 45 degrees because the object itself is rotated by 45 degrees. Okay, so I should add 45 to all of them. Then 50. You people are understanding or not what exercise I am doing here?
Yes.
60. And we can add actually 125 and then 90, 105, 45, right? 115, and then 135, 165. Okay, so now the magnitudes will be same because actually for the rotated object, okay, if you see previously the magnitude which was there at say 90 degrees, now sorry, which was there at probably 120 degrees, okay, which is something odd, is 100. Now the same magnitude will occur at 165 degrees. Okay, so the magnitudes doesn't change. So you see dominant direction, this edge itself has rotated. So edge magnitude doesn't change. Edge magnitude here and here are same, except that the angle of edge is changing. Okay, so if I consider previously the reference direction, okay, so the reference direction for the previous image or pixel, if I can, previous object is like this, previous patch is like this. Oh, sorry, previous patch reference direction is like this. Anyway, whatever I have plotted here, this is the reference direction. Okay, now the reference direction is like this. Okay, so if I sketch again the HOZ, take the same value, we get the same values here. 5, 10, 2. I'm just writing here, but I hope you understand. Now, if I sketch the HOZ, what will happen? 0, 22.5, 45. Okay, you can sketch the HOZ. I will skip sketching it in the class now. Okay, but what you can see now after sketching it is the peak will occur now instead of at say 60 to 90 during this bin. The peak will occur in this bin now. Okay, 112 to 135 bin. So previously it was 78.75. Now since we have rotated the object itself got rotated, or the key point, the information about the key point got rotated by 45 degrees, okay, in this direction. So what will happen if I consider this is the 90 degrees previously, okay, now this is 125, 90 plus 45 degrees, that is 125 degrees. It will be close to the dominant direction, you check, okay, our reference direction given by the dominant HOZ value, HOZ, dominant value in HOZ vector. Okay, dominant value in HOZ vector is close to what angle? 78.75 plus 45 degrees. Okay, which is equal to how much? How many degrees? 123.75. Okay, hope this is understood. Now what we do is we subtract this reference angle from each of these angles, okay, to get the HOZ representation. So what will happen in that case? See, in this case, the reference angle is say 78.75 plus 45. Okay, so this is this. See, each time we get the same object will be there, but it will be there with different orientations. So what we do is by subtracting the reference orientation from the original image, what we are ensuring is we are representing the patch information or the key point information with reference to the a particular standard orientation, that is zero orientation itself. Or we are representing the information of the key point, okay, with respect to invariant to the rotation. Okay, because this say the key point information is still retained, but it is obtained with respect to whatever the reference angle, dominant angle, we are subtracting from all angles in representation of HOZ now. So what this is represented is, so in the first case also what we do, this HOZ from the HOZ vector, which is like this, what we do is now we, since the dominant angle is 78.75 and so on, we subtract the 78.75 degrees from all these angles. So 0 will be represented as 0 minus 78.7, 0 is represented as 0 minus this one. Similarly, 45 degrees will be represented as 45 minus 78.75 degrees and so on. Okay, so we, with respect to this reference angle, we represent here the HOZ vector. Okay, similarly, even here, what we do in this case also, 0 is represented as 0 minus 123.75 degrees. Here, 45 degrees is represented as 45 minus 123.75 degrees. So with respect to the reference orientation, we represent the HOZ vector. So that what happens, there is a circular shift in these values. So some of the values will come in different locations now. Okay, but this vector, this HOZ vector and the HOZ vector corresponding to this and this will have the same values. That is the advantage. So any patch corresponding to the same key point will have the same HOZ vector. Okay, here if you, but if you directly take without reference orientation, this will get another HOZ vector. This is HOZ vector 1. If I consider this HOZ vector 2, both are not same. HOZ 1 is not equal to HOZ 2 without subtracting the reference orientation. If I subtract the reference orientation, HOZ 1 is equal to HOZ 2. Okay, that's how they represent. Hope this is clear. Okay. So the last step that they follow in matching is they remove the ambiguous matches. They only consider unambiguous matches. Say once you do all this, we get reasonable number of key points. Okay, and then their descriptions. Okay, so we get the key points with the different scales. Okay, and then different with respect to difference orientation vectors, reference vectors. Okay, and then we get the orientation subtracted, or the reference orientation subtracted HOZ vectors for each key point. After getting the HOZ descriptor for say key point 1 and key point 2 and key point 3 in one image, and if we get the same in another image, say there are other key points, point 1, point 2, okay, point 3 and point 4, etc. in other image. Okay, now what we would like to do, we would like to see if these points are this object and this object is same or not. We would like to see in general. Okay, object described by these key points, object described by these key points are same or not. Or this key point and this key point, is it describing the same information? Okay, these are the questions. To do that, we may establish a matching or a correspondence. Around, say you have actually descriptor 1 here. So HOZ 1 for the, say 1, 1 I say for image 1, HOZ 1, 2, HOZ 1, 3. For image 1 and point 1. Image 1, point 2, image 1, point 3. Similarly here HOZ 2, 1, HOZ 2, 2, HOZ, okay, 2, 3, HOZ 2, 4. Now what I need to do, I will perform all the combinations of matching and see which is the nearest neighbor, which is a good match. Assume that this is a good match for this. Okay. Similarly, I see that, say the good match for this So if I consider this as the good match for this, okay. Similarly, if this is the good match for this and this is the good match for this, then these are the three match key points. Now these are referred to as nearest neighbor key points. See, for this is a good match, fine. But the second good match is this. This is the second good match. Okay. So the distance, this distance is D minimum. Okay. But this is D minimum next to D minimum. Okay. D minimum 2. Then what they try to see to locate an ambiguous match is D minimum 1 by D minimum 2. Okay, usually if this is, say if both are very close, the first point is very close, fine. Second point is also close to this. Then what does it mean? Okay, the D minimum 1 by D minimum 2 is close to 1. If this is D minimum 2 is much different than D minimum 1, then what will happen? This will be, okay, less than 1. Is it not? That means D minimum 1 will be very small. The first minima is very small. The next minima will be, okay, little farther. So in that case, this is less than 1. So ambiguous matches are those for which the ratio of distances of the first nearest neighbor 1 by nearest neighbor 2, okay, distance of nearest neighbor 1 by distance of nearest neighbor 2 is greater than 0.8. Okay, so those are ambiguous matches, doubtful matches. Those they eliminate. They do not take into consideration while matching. Okay, this is the last step in scale invariant feature transform. With this, they get the reliable matches and they demonstrate very well on different computer vision tasks. So in the next class, we will see some of the slides describing these things and then move on to the other topics of computer vision. Okay, hopefully 2 weeks. So we'll take to complete the discussion on computer vision aspects and then move on to the deep learning. If you have any quick questions, you can ask now. Okay, thank you then.